In this video, we will discuss organic synthesis, which is taking simple organic compounds that you may be able to purchase or find in nature to make more complex organic compounds that might be of interest in medicine or for other academic purposes. Our learning goals for today are to be able to propose a multi-step synthesis using substitution, elimination, and electrophilic addition reactions that we have learned this semester in Organic Chemistry 1. We won't be learning any new reactions today. We will simply be discussing how to sequence those reactions that we do know in order to make some desired product, given some starting material. So perhaps it involves a substitution reaction and then an electrophilic addition reaction. Oh, and then maybe there's an elimination. Who knows what the particular reactions will be? That will vary given the desired product and the starting material. So today we will practice synthesizing what we've learned this semester, not only the reactions that we've learned, but also aspects of stereochemistry, regiochemistry, so reactivity, acidity, basicity, and other topics, all as applies to making complex organic molecules. To recognize synthetic traps are essentially unexpected reactions, which happen all the time, that prevent a desired product or a desired intermediate of a synthesis from being formed. For example, let's imagine we propose some reagents to convert A into B. But there was something we overlooked, some aspect of this reactivity we overlooked, and B is not observed. Some unexpected product is observed. Well, then we need to rethink the conditions proposed for that particular reaction, or maybe even propose a new synthetic pathway. Next, we will distinguish between functional group transformations and reactions that alter the carbon skeleton, which will help us in proposing these multi-step syntheses that we're working towards. We will analyze synthesis problems with a way of thinking called retrosynthetic analysis. This is an extremely powerful way to approach synthesis problems. We will use retrosynthetic analysis to come up with these schemes in the first place by asking ourselves, what can the desired product be made from? What functional groups does it have? What functional groups is it made from? So thinking backwards. Finally, we will evaluate the efficiency of two synthetic schemes based on percent yield, toxicity, safety, and waste production. These last three are features of what is often referred to as green chemistry or environmentally friendly chemistry. With that framework, let's go ahead and get started. Humans have been consuming medicinal herbs and plants for thousands of years. For example, cloves and peppermint have been consumed for their local anesthetic properties. You may have taken a menthol cough drop before. It eases the pain in your throat when you have a sore throat. And that is because the herb peppermint contains a compound called menthol, and that particular compound has these anesthetic properties. Eventually, the action of most or all of these medicinal herbs and plants have been attributed to natural products. Menthol is an example of a natural product. It is the specific chemical entity in the herb responsible for its medicinal properties. Natural products are made in nature, made by plants, for example. Since the 1800s, chemists have attempted to synthesize or make these natural products and other molecules similar to them from readily available molecules. I often joke about molecules available from the chemical store, but what I mean by that is simply what we stated at the beginning, that a synthetic chemist takes simple molecules and then converts them to more complex molecules of interest. I hope that you're starting to see what some of these complex molecules of interest might be. They might be these natural products that have medicinal properties that are contained in herbs or plants that people have been using for thousands of years. It's impractical to obtain these medicinal natural products from the herbs or the plants because would involve a lot of herbs and a lot of plants. And we'll discuss that a little bit more in a moment. Before we do, I would like to show you some of the natural products that have been made by synthetic organic chemists. Note the stereochemistry, note the complex ring systems, note the number of atoms, and these really amazing compounds that are both found in nature and have been made by synthetic organic chemists. We've discussed menthol, which is a natural product that comes from an herb, peppermint, and has anesthetic properties. Let's think about another natural product now that comes from a different plant. Inflammation, which is a highly important biological response to protect and repair the body, has been understood for over 2,000 years. Inflammation can cause fever and pain. The ancient Greeks described how the bark of the willow tree was used to treat inflammation, so to relieve pain and fevers. The bark of the willow tree is an example of a medicinal plant. Analysis of the bark of the willow tree showed, and it was well understood by the 19th century, that the active ingredient, the natural product that was responsible for the anti-inflammatory effects of the bark of the willow tree was a molecule called salicylic acid. In the 1800s, doctors regularly prescribed salicylic acid to relieve pain and fever. So it was isolated from the bark of the willow tree and it was regularly prescribed to treat inflammation. However, salicylic acid is very irritating to the stomach, so it is not ideal as a treatment for inflammation and is no longer used. This is primarily due to the work of German chemist Felix Hoffmann, who synthesized acetylsalicylic acid, a derivative of salicylic acid, in 1897. Acetic anhydride delivers this acetyl group, replacing the phenol hydrogen. Acetylsalicylic acid is much less irritating to the lining of the GI system. This process represents a synthesis. A simple molecule found in nature was reacted with another simple molecule to form a more complex molecule of interest. This molecule is of interest because it relieves inflammation without the side effects of being irritating to the GI epithelium. The pharmaceutical industry is a huge industry, and this compound, acetylsalicylic acid, has been marketed by Bayer ever since. So this is aspirin. You've probably consumed it before. Fun fact, aspirin was used in the 1918 flu pandemic to relieve the dangerously high fevers that were associated with that infection. Acetylsalicylic acid was so successful at relieving inflammation that chemists continue to modify the structure of salicylic acid in different ways in hopes of discovering molecules with even better anti-inflammatory properties with fewer side effects. You are likely familiar with at least two of the compounds that resulted from these studies, one of which is ibuprofen, which goes by the trade name Advil. The other is naproxen, sold under the trade name Aleve. You can see that both ibuprofen and naproxen are chiral. Ibuprofen is sold as a racemic mixture. Only the S enantiomer of ibuprofen is effective, but the R enantiomer is inert. However, naproxen is sold as the pure S enantiomer because the R enantiomer causes liver damage. This field of synthesizing compounds that are used as medicines is called medicinal chemistry. And if you're interested in it, you might study organic chemistry to become a medicinal chemist. A medicinal chemist is a synthetic chemist. They make compounds and they have to use all of the ideas and concepts about structure and chemical reactivity that you've been learning this semester. A medicinal chemist needs to isolate one enantiomer of naproxen. And you can imagine how difficult that might be, since two enantiomers have all the same properties, except how they interact with other chiral substances. Well, I could talk about this forever, but let's move along. We'll discuss one more natural product called Taxol. With just one look at Taxol, we can see this molecule is much more complicated than any of the medicinal compounds we've previously discussed. Acetylsalicylic acid, ibuprofen, naproxen. When I say more complicated, I mean it has more atoms and it has many stereocenters. As you may imagine, it is only this stereoisomer of Taxol that has these desired cytotoxic effects. Cytotoxic means that Taxol kills cells. Why would we want that? Well, we would want that for treatment of cancer. So Taxol is used to treat metastatic ovarian and breast cancers. Thinking about the stereochemistry of Taxol, there are 11 stereocenters. So 2 to the 11 stereoisomers of Taxol exist, and the synthetic chemist must make Taxol as a single stereoisomer. That's 2,048 possible stereoisomers of this compound. Now, Taxol was discovered in the 1960s during an effort to find cytotoxic compounds from plant extracts. There is a theme. Humans use plants and herbs and even marine organisms to treat human disease because there are medicinal compounds in those natural substances. So this organized effort, what it means is that chemists would go out and they would gather things from nature. They could gather things from the ocean, herbs, mushrooms, all kinds of things from nature, put them in a blender, and they use extraction to remove the organic compounds from those things from nature, and then TLC or methods like TLC to separate all the different compounds that were in the extract from that natural substance, that plant, that sponge, that herb. And then now once the individual compounds are in hand, those individual compounds are tested against cell lines. So the cell lines are just given those compounds, and then the biologist or the medicinal chemist would look to see if the cells die. So if that compound kills cells, it's cytotoxic, and then chemists and biologists continue to study it. And if it's deemed of interest, an organic chemist might try to make it. I mean, think about Taxol here. Taxol was isolated from the bark of the Pacific yew tree. It takes one Pacific yew tree, the bark of that tree, to get 300 milligrams, so that's less than a gram, right, of Taxol. One tree for that much Taxol. Think about all the trees that would have to be grown and then killed to isolate Taxol from these trees to use as medicine. It's impractical. And to solve that problem, synthetic chemists have made Taxol. There have been many, many syntheses of Taxol, Taxol being the complex substance from simpler substances that one can buy at the chemical store. The first synthesis was published in 1994. It involved 46 chemical reactions and 12 years of work by graduate students. The simpler substance that was converted into Taxol is camphor, which is itself a natural product. Well, where does camphor end up in the molecule? Well, we can find the methyl groups from camphor, certainly. So the geminal dimethyl, 2 methyl groups on a single carbon. We can see that carbon in Taxol. So 46 chemical reactions, 12 years of work. Why would anyone do this? Well, to say you can, it feels good to make something, to achieve a difficult academic problem, but also capitalism, total sales of Taxol and compounds like it was $4 billion annually in 2000. So this is a huge industry, medicinal chemistry and synthetic chemistry. Some would argue that it's an industry on the decline, but that is a topic for a different time. Let's revisit our learning goals for a moment. Have we achieved any of these yet? No, we've just done a lovely introduction by yours truly. Okay, check. Now let's move in to this third learning goal, distinguishing between functional group transformations and reactions that alter the carbon skeleton. Functional group transformations are exactly what they sound like. It's a step, such as this substitution step, where the functional group is changed. We begin with an alkyl bromide, treat with sodium hydroxide to generate an alcohol. The carbon chain remains exactly the same, only the functional group was altered. So this is a functional group transformation. This is in contrast to a carbon skeleton altering step. Let's imagine that we take that same alkyl halide, but this time we treat it with sodium cyanide. This also proceeds by an SN2 mechanism, just like the reaction that we looked at here, which was a functional group transformation. But this time we've altered the carbon skeleton because we're making a carbon-carbon bond. There are 3 carbons, and this carbon-carbon bond has been made. Those are our 2 types of synthetic steps. Let's pause and take a moment and label each of these steps in the synthesis from this epoxide to this aldehyde as either functional group transformations or carbon skeleton altering steps. If you haven't attempted these problems, go ahead and do so before listening to my solutions. In step 1, an epoxide is converted to the vicinal alcohol ether shown. But the carbon chain remains the same as shown in pink. There's no changes to the carbon chain here. So this is a functional group transformation, which we'll abbreviate as FGT. For step 2, if we look at the starting material going to the product, we can see that the change is the alcohol being converted to an alkyl bromide. The carbon chain remains exactly the same as indicated in pink. So again, this is simply a functional group transformation, converting an alcohol into an alkyl bromide. For step 3, we notice that the alkyl bromide is indeed converted to an alkyne, but in doing so, a carbon-carbon bond was made, as indicated in pink. So now the carbon chain has changed. There's a branch here consisting of that alkyne. So this is a carbon-carbon bond forming step. In step 4, the alkyne is converted to an aldehyde. I will number the carbons to be sure that no carbons are being added or removed from the structure. So we can see the number of carbons hasn't changed. The carbon chain is the same. So this is another example of a functional group transformation. Alkyne to aldehyde. Finally, in step 5, we notice that this bond was made. That bond represents a carbon-carbon bond. Now the carbon skeleton has changed, as indicated in pink. There is a new 2-carbon branch. Thus, step 5 represents a carbon-carbon bond forming step, or a carbon skeleton altering step. Now that we can identify the functional groups, identify the types of steps, carbon-carbon bond forming versus functional group transformation, let us stop and practice. We'll propose the reagents needed for each of these steps. And the first step for proposing the reagents is indeed to identify functional groups. So we've done quite a bit of the work already. Please pause the video and practice this. This is excellent preparation for the upcoming final exam. For this first step, converting an epoxide to the vicinal alcohol ether, we should stop and look at what carbon of the epoxide reacts. It is carbon 1. This bond, indicated in purple, is formed. When we see that it is the less substituted carbon of the epoxide that does the reacting, right? Carbon 1 is less substituted than carbon 2, and carbon 1 has made a bond to the alkoxy group. Once we've recognized that, we understand that this epoxide was opened under basic reaction conditions. Delivering the methoxy group under basic conditions means that this epoxide was treated with sodium methoxide. This is a strong nucleophile which will react at the most available, the least sterically hindered carbon in a pure SN2 fashion. Typically, we also include the conjugate acid of the alkoxide base as the solvent. One reaction down, a few more to go. Let's take a look at the second step of this transformation, where, as we've previously stated, the alcohol functional group is converted into an alkyl halide functional group. There are several ways that we can achieve this transformation. However, we will need to turn hydroxyl into a good leaving group such that the overall substitution can occur. Alcohol to alkyl halide by an SN2 substitution can be achieved with phosphorus tribromide. Or we could have converted the alcohol to a tosylate, which is a good leaving group. Then we can treat with sodium bromide, which delivers nucleophilic bromide, electron-rich bromide, that displaces the tosylate, primary tosylate after all, in an SN2 reaction. We could not take the alcohol and just directly treat it with sodium bromide. Hydroxyl is not a good leaving group, so bromide will not displace hydroxide. No. Hydroxide is a strong base. It is the conjugate base of water, which has a pKa of 16. So we do need to convert hydroxyl into a good leaving group, which we can do with phosphorus tribromide or by using the tosylate intermediate. So there are two ways to achieve step 2 or transformation 2. Oh, very interesting. Both step 1 and step 2 are substitutions that go by SN2 mechanisms. So remember, one of our goals today is to propose multi-step syntheses using the reaction patterns that we've previously learned in the course. Transformation 3 is that carbon-carbon bond-forming transformation. This bond is being made. As you know, in most reactions, there is an electron-rich atom and an electron-poor atom that come together, share electrons, and make a bond. We know that alkyl halides are a source of electron-poor carbon. In other words, they're electrophiles. Taking a look at the product for a moment, if this carbon indicated in pink was the electrophile, then the other atom bonding to it must have been nucleophilic. Thus, this bond was made from the acetylide ion reacting in another substitution reaction, so specifically an SN2 by an SN2 mechanism, with the alkyl halide starting material. So how do we write out the conditions for this transformation? We can simply use sodium acetylide. We'll just note that carbon is electron rich, it's a nucleophile. So yet another substitution reaction. Of course, it's also a carbon-carbon bond forming step. As we said, it alters the carbon skeleton. Let's move on to transformation 4, where the alkyne is converted into an alcohol. Another functional group transformation. How do we achieve alkyne to alcohol? Well, it's very important that we make use of our reaction chart, either our mental reaction chart that we've memorized and have in our brain, or, well, a physical reaction chart that's in front of us. So we know that we're attempting to make an aldehyde. So we would scan our reaction chart looking for the aldehyde functional group in the products. And right now, we're in a lovely time where we really don't know many ways to make aldehydes. We know how to make them from terminal alkynes. Let's check and see if that's the starting material we have. Yes, it is. This is a terminal alkyne. So we know how to convert the terminal alkyne into the aldehyde. We know how to convert a terminal alkyne into an aldehyde. And if we don't, we're going to consult our reaction chart, and we will see that these reagents are used. A bulky borohydride is used. Specifically, we can use a reagent called 9-BBN, 9-borobicyclononane, which as I draw it, you can see how bulky those R groups are, hopefully. So this part of the molecule, that is the R2. So yes, you can see it's very bulky, right? R1, R2. They just happen to be connected. Here's the reactive BH bond. So this is an example of a note that you may make. You may also choose to number the carbons and make a note about the selectivity of the reaction. There is a net addition of water across the 2 carbons of the alkyne, where the oxygen makes a bond to the less substituted carbon. You may also note that the reaction proceeds via the enol. Clearly see this addition of HOH, water, across those 2 carbons of the alkyne, and then an enol keto tautomerization occurs. Finally, you could note that this reagent can also be used for internal alkynes. Now, the aldehyde will not be observed, the ketone will, since there's an R group instead of an H. So again, for an internal alkyne, there's R instead of H. So instead of an aldehyde, there would be a ketone observed. However, we would just want to beware if the internal alkyne was asymmetrical. So the example that I gave you, the 2 R groups are the same. So this is a symmetrical internal alkyne. But in the case of an asymmetrical internal alkyne where the 2 R groups are different, then we will observe 2 different products since the 2 different carbons of the alkyne have the same substitution. Although all this information might be on your reaction chart, you may not need it all every single time, but it's good to have it there. So your reaction chart will be invaluable to you as you solve synthesis problems such as this one. So we'll use hydroboration oxidation to convert the alkyne into the aldehyde. So that functional group transformation is achieved, and there's one more step to get to the product of this synthetic group. That's the final step, which I'll label 5. In step 5, as we've already discussed, a carbon-carbon bond is formed. This 2-carbon chain is installed to the alpha carbon of the aldehyde. Well, this will be an alpha alkylation. We know that we can use a strong base to deprotonate the alpha carbon of an aldehyde or a ketone. That generates an enolate, which I've drawn in its most contributing resonance form, but we could consider both resonance forms of the enolate, and that might help us to remember why enolates are nucleophilic at the alpha carbon. So alpha carbons are nucleophilic. If this bond was made, that means that this carbon was electrophilic. So what is an electrophilic source of carbon where the leaving group leaves? Yes, it's an alkyl halide. So we'll deprotonate the aldehyde with lithium diisopropyl amide at negative 78 degrees Celsius, and then treat it with the 2-carbon source, so ethyl bromide. There are no mechanisms in synthesis questions, but we can just be sure that we remember the mechanism for this transformation. I'll use the more stable resonance form of the enolate and show you how the enolate acts as a nucleophile from the alpha carbon, making, for this little example, this carbon-carbon bond. There we go, 2 carbons, the bond is made. So this is just, on the side here, this is just a simpler example, smaller molecule than the one we're given. A few notes before we move on about formatting, and we will use this example here for the first step. So for the first step, we wanted to use methoxide to open up the carbon-oxygen bond in the epoxide. But we didn't just list methoxide itself as the reagent because there's not a bottle of anions. So we listed sodium methoxide. That is the reagent we buy at the chemical store. So we do need to use the counter ion. In this case, it was sodium to go with anions that we use. We can see again in step 3, we use sodium acetylide, even though it was the acetylide ion itself performing the SN2 reaction. So be sure when you're proposing the syntheses that you're using reagents, not just the reactive species in the mechanism. So in this case, a acetylide ion would have to have a counter ion, and that would be sodium. So sodium, potassium, would be okay. Excellent. Well, this synthetic route was proposed for us, right? The intermediates were outlined, and we filled in the reagents. But we could be given some starting material and then fill in or provide the structures of all these intermediates so that we would be able to, if told, this is a desired product, this is your available starting material. We want to propose all the reagents and the intermediates necessary to get to that product. Yikes, how will we do this? It sounds hard. It is challenging. We will use a specific way of thinking in order to propose these synthetic schemes. That way of thinking is called retrosynthetic analysis. Just as the name suggests, we'll be thinking backwards. In fact, this way of thinking won a Nobel Prize in Chemistry in 1990 for Professor E.J. Corey, who is a synthetic organic chemist at Harvard University. What? A way of thinking won a Nobel Prize? Yes. It's because Professor Corey used that way of thinking to make many, many natural products and derivatives of natural products of interest. So you'll see Professor Corey's name many times on this slide. Corey, 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 Corey. And that's because he took this way, Corey, he took this way of thinking, retrosynthetic analysis, and applied it to these really tough problems in organic synthesis. So in retrosynthetic analysis, we will look at the desired product and identify functional groups, and then ask, well, what can I make those functional groups from? So this arrow represents the thinking backwards. So what can these functional groups be made from? Well, in this case, that would be whatever D is. Okay, well, what can I make D from? Oh, I can make D from C. I can make C from B. I can make B from, yes, the starting material that's available to me. Let's practice now with a desired product, looking at the functional groups and bonds in that desired product and asking ourselves, well, where does this come from? How do we make this? And going backwards and backwards and backwards until we come to chemicals available at the chemical store or those that are available to us given the parameters of the problem. Retrosynthetic analysis requires that we have our organic chemist toolset, aka our reaction chart, at the front of our minds so that we can be using these reactions. So we know, oh, terminal alkynes, so that we know, oh, aldehydes, those come from terminal alkynes. So if you were given some aldehyde and asked to make it, say, okay, aldehyde, well, these 2 carbons, those could have come from a terminal alkyne, and perhaps this terminal alkyne is available at the chemical store, and then you're done. Yay. All right, let's practice that process now. So here's our first desired product. It is an alkyne. We are going to make this alkyne from compounds containing 2 or fewer carbon atoms. Yike! How many carbon atoms are in the starting material? Yes, 5 of them. However, the available starting materials may contain 2 or fewer carbon atoms only. So not only should we identify the functional group in this molecule, which is an internal alkyne, and ask ourselves, what functional groups can internal alkynes be made from? We should also be thinking about which carbon-carbon bonds were made to get to this product. Now, because we have our synthetic toolbox in our brains, we know, or on paper, and we're looking at it, we know that a terminal alkyne can be deprotonated with a strong base, such as sodium hydride. This generates a nucleophilic acetylide ion, where the carbon atom of the alkyne is electron rich. This can be treated with an electrophilic species, such as an epoxide or an alkyl halide. In an SN2 reaction, this generates a new carbon-carbon bond. Perhaps we can use this reaction to generate the internal alkyne of interest in this particular problem. So we've identified that internal alkynes can be made from terminal alkynes. So perhaps the desired product came from an acetylide ion, so thinking about breaking this bond right here, and methyl bromide. Okay, so our final step would be this SN2. This acetylide ion would have come from the terminal alkyne. Well, let's just take a moment. This starting material has 1 carbon, but this has 4 carbons. Our available starting materials may have 2 or fewer. So methyl bromide is okay. We can use that, but we cannot start from here. There are too many carbons. No problem, right? We can break this bond between the alkyne carbon and that alkyl chain. In the same process, imagine using the acetylide ion and this 2 carbon piece. So carbons 1, 2, 1, 2. If we look back at the desired products, carbons 3 and 4 are the alkyne carbons. So here they are. And then that methyl, that would deliver carbon 5. Great, we have our plan now. So now that we have our plan, our retrosynthetic analysis, we can write out our proposed synthetic route, aka your answer. Be sure that we keep in mind that all of our available starting materials may contain 2 or fewer carbon atoms. All right, so we're going to start from, there's nothing that prevents us actually from just starting with the acetylide ion. So let's just take these 2 pieces. Let's take ethyl bromide and treat it with sodium acetylide. There's nothing that prevents us from doing that in the parameters of the problem. Good. So this generates the 4 carbon intermediate. So we are here right now. Okay, so now we need to go from here to generate the nucleophilic species for the second alkylation. So to do that, as we identified above, we need to deprotonate the terminal alkyne with sodium hydride or sodium amide, an appropriately strong base. I'll use sodium hydride. That will generate this sodium acetylide intermediate. We will treat that with, just as we said, with methyl bromide, because now we are here in our plan, so we need to go the final step. We'll treat it with methyl bromide, which will generate that last carbon-carbon bond. And we did it. We've made our desired product. And now we just double check. Let's double check that we used starting materials that fit the parameters of the problem. So we could use compounds containing 2 or fewer carbon atoms, and we did that. 2 carbon atoms, 1 carbon atom, 2 carbon atoms. So all of our starting materials are good. They follow the parameters. Make sure that we didn't throw any random ions in. Everything has a counter ion. So we have sodium acetylide, perfect, sodium hydride. And we didn't invent new chemistry. We were logical, we were rational, we thought backwards, and we used reactions we've discussed in class. Let's try again. That was fun, right? Okay, so let's use retrosynthetic analysis to propose a synthesis of this desired product from the given starting materials. And so this can be very fun. You know, that wasn't sarcasm. This is fun. Treat it like a puzzle and convince yourself it's fun. But I think that it won't take much convincing. So here, this desired product should be made from benzyl bromide, this molecule, plus any reagents with 3 or fewer carbon atoms. Okay, so let's just see if we can identify benzyl bromide in the desired product. Where might that starting material end up? Well, there's 2 places. There's this group and this group here. Let's be absolutely sure that we understand what I mean by benzyl. Benzyl is the phenyl ring with a CH2 attached, and it's attached to something. So benzyl. So this is benzyl bromide. And the other atoms in the desired product are right here. Let's count them up since we are given this caveat that our starting materials may have only 3 or fewer carbon atoms. And we'll find that there are 3 carbons in this piece. Cool, now let's identify functional groups. Sweet, there's a ketone. And we can see that the bonds to the benzyl group were made at the alpha carbon of the ketone. Awesome. In our minds, our reaction chart should be alerting, alert, alert, alert. We've figured out which reaction will be used to generate this molecule. Yes, it's the alpha alkylation of a ketone. So these 2 examples that we've considered using retrosynthetic analysis for actually are both quite hard because the key step is a carbon-carbon bond forming step. For this synthesis, we will look at the alpha alkylation. For the previous synthesis, the reaction of interest was alkylation of the terminal alkyne. So in both cases, the key steps were carbon-carbon bond forming steps. It's actually a bit easier to identify, I think, key reactions when they involve functional group transformations. So it's good. We're tackling the hard examples first, and we'll take a look at some easier ones or maybe some more obvious ones that involve functional group transformations as we practice and as you practice on your own. All right, so we're going to use the alpha alkylation of a ketone. Your reaction chart entry may look like this. You may have labeled somewhere that it's a carbon-carbon bond forming step. Organic compounds are made out of lots of carbons, particularly the ones of interest. Think about all these medicinal natural products from the beginning of the lecture. Many, many carbons. And the chemicals that you can buy at the chemical store have fewer carbons. So these carbon-carbon bond forming steps are really good to have in your head because they'll be key steps often in synthesis problems. So alpha alkylation of ketones is one of those carbon-carbon bond forming steps. We know that this occurs via the enolate. So strong base, lithium diisopropylamide, is used to generate an enolate. As we mentioned, enolates are nucleophilic at carbon. And we can especially see that in the minor resonance form. So they're nucleophilic at carbon. Carbon is electron rich. So enolates can be treated with electrophiles such as alkyl halides, shown here. So where the alpha carbon of the alkyl halide is electron poor. To generate carbon-carbon bonds, these alpha alkylated products. So alkylation happens at the alpha carbon. You might have additional notes about alpha alkylation in your reaction chart because for asymmetrical ketones, alkylation can occur either via the kinetic enolate or the thermodynamic enolate, such that both constitutional isomers resulting from alkylation may be formed. So through the kinetic enolate, a bond can be made to the less substituted alpha carbon. And via the thermodynamic enolate, a bond could be made to the more substituted alpha carbon. Okay, now we're armed with our information. So let's go ahead and draw out the retrosynthetic arrows. All right, so let's take it one bond at a time. So if we imagine disconnecting at one of these bonds that's made between benzyl bromide and the enolate, we would get this species, or these reactive species, right? So nucleophile, electrophile, We probably didn't start with the enolate, so you have to think about where that enolate came from. That enolate came from this ketone that was deprotonated with LDA. Now, I know the conformation is funny. I'm just keeping it in the same shape as the product. Okay, now keep thinking backwards because we can only start with starting materials of 3 or fewer carbons. We must have made this other bond to the alpha carbon, all right, via this enolate. And I'll just draw the minor resonance form here and benzyl bromide. All right, so we're good. So now we're at allowed starting materials. So here, there was our thinking backwards, how we're going to generate the product. And now let's think in the forward direction. Let's write out our synthetic route. If you feel comfortable, I highly encourage you to write out your synthetic route in the forward direction and then compare with mine. We'll go ahead and pause if you'd like to do that. For first things first, we need to generate this active enolate species. We're going to start from acetone and treat it with LDA and -78. We don't need to worry about the number of equivalents or anything like that because this is a symmetrical ketone. Second, we're going to treat with the electrophile. Since all we're doing in the first step is deprotonating, you can combine these two steps, but typically you would write out every intermediate. But this one is an okay one to combine. And again, I'm going to write the intermediates out in the same conformation as the product. I am also going to abbreviate the phenyl group. So phenyl is just the benzene ring. So this is phenyl. All right, now we've made most of the molecule. We've made one of those new carbon-carbon bonds right here. Okay, so that's this one. And now we're here. So we need to generate this enolate, treat with benzyl bromide, and that will form our final carbon-carbon bond and lead to the desired product. How should we do that? Yes, the same exact way as we did in step 1. We're going to treat with LDA, and then we're going to treat with the enolate that's formed with the electrophilic benzyl bromide. Okay, so treating with LDA generates the enolate. Phenyl bromide or benzyl bromide delivers the electrophile. They react, and then we form that key carbon-carbon bond. What do you think? Have we overlooked anything here, or are we good to go? Yes, in this second alkylation step, it is proceeding via this enolate, which results from deprotonation at the more substituted of the two alpha carbons, two different alpha carbons that this ketone has. So we need to pay attention to this aspect of our reaction chart where we were discussing how the amount of LDA could be used to favor either the kinetic or the thermodynamic enolate. LDA is a bulky, strong base that typically deprotonates at the least sterically hindered carbon. In the case of ketones, deprotonating, let's take a look at this one, zoom in. So deprotonating at the less sterically hindered alpha carbon would make the kinetic enolate. To make the kinetic enolate, you use just a bit more than one equivalent of LDA to ensure complete deprotonation of that carbon. To make the thermodynamic enolate, or the more substituted alkene enolate, which is what we want here, want to deprotonate and eventually alkylate at the more substituted of the two alpha carbons of this ketone, so this enolate. And the minor resonance form, we can't really see that this is the ene part. So let's draw that out. Okay, this is the more substituted enolate. So in this case, we do need to use just a little bit less than one equivalent of LDA. What this allows to happen is it allows equilibration. So initially the kinetic enolate is formed, but because we didn't use a full equivalent of LDA, there is some of the unreacted ketone left, and basically equilibrium can be reached. The more substituted enolate can be formed. You don't have to worry about too much how that happens. Let's just keep in mind, that a little less than 1 equivalent of LDA can generate the thermodynamic enolate. All right, so we'll use this aspect of the alpha alkylation to complete this synthesis. So because the second alkylation does proceed via the thermodynamic enolate, we will indicate that it is just less than 1 equivalent of LDA that is necessary for this transformation. We did it! Not so bad when we read it out in the forward direction, right? So most of our work was the thinking. The retrosynthetic analysis, the thinking backwards, that was the hard part. But we were able to develop that plan using our knowledge of chemical reactivity and how structure affects chemical reactivity. Now, we developed a good plan. However, sometimes there are multiple plans that can be proposed for a given synthetic problem. For example, this is a synthetic problem that we've just encountered. And on the top of this slide, I've written out the synthetic route with the plan that we have just proposed. We proposed a series of 2 alpha alkylations. First, to generate this carbon-carbon bond, and second, to generate this carbon-carbon bond. I've numbered carbons, and I've mapped out where the benzyl group from benzyl bromide shows up in the intermediates and the products. So you may pause and familiarize yourself with that. In addition to our plan at the top of the page, it is reasonable to expect that someone may come up with a different plan. So here's a different plan down at the bottom of the page. We'll call it plan number 2. Plan number 2 identifies the alpha alkylation that was identified in plan number 1. So the final step would be the same. Where slightly less than 1 equivalent of LDA is used to deprotonate at the more substituted of the 2 alpha carbons of this ketone. That enolate reacts with benzyl bromide, this reagent here, to install this piece. Excellent. Plan number 2 differs from plan number 1 in this second key disconnection. The student who came up with this plan identified the ketone functionality in this key intermediate and thought about their reaction chart and maybe scanned it and thought about the functional group interconversion from an alkyne to a ketone and thought that might be a good way to install those 3 carbons, right? That student knew that the benzyl group most likely comes from benzyl bromide. So perhaps a way to install the other 3 carbons is from an alkyne. And we could definitely consider doing that, right? Because the benzylic carbon of benzyl bromide is electron poor, it is electrophilic. And we could deliver what I've labeled carbon 3 here as an acetylide ion. It's nucleophilic, it's electron rich. So this all seems somewhat reasonable. We could take the alkyne and convert it to the ketone using oxymercuration conditions. And then we would just mix these 2 species together to form the internal alkyne. All right, so we have 2 plans here. Which one is better? Which one should we use? Which student is correct? Well, we can evaluate multiple synthetic routes in many different ways. So just to be clear, we have some desired product. We'll call it compound Z. And we may start at the same starting material, or you could imagine starting at different starting materials. Let's say for this example, we'll start at different starting materials to get to the same product. So there's 2 routes again in this generic example, plan 1 and plan 2. There are several metrics by which we can evaluate which route is better. One of them is efficiency, especially as related to cost. We might attempt to maximize the overall percent yield of Z. To do this, we can either minimize the total number of steps. So in plan 1 here, there are 3 steps. In plan 2, there are 4 steps. Now you may think, so what? 3 steps versus 4 steps. If all 3 steps proceeded at 90% yield, which would be an excellent synthesis, you'll find then the laboratory synthetic steps often occur at lower yields. The overall percent yield of the reaction of this whole sequence from A to Z would be about 73%. However, for plan 2 with 4 steps, again, let's imagine they all go 90% per step. Overall, from D to Z, the total yield would be about 66%. The more and more steps you have, the more and more dramatic these differences. So we can look at the total number of steps. Now, of course, let's imagine that plan 1 has a step with a 50% yield. Say its first step is 50%, and then the other synthetic steps are 90. For plan 1, with that first step at a 50% yield, you'd have an overall 41% yield from A to Z. Versus if plan 2 had 90% yield for each step, you'd have 66% overall yield. And this time, plan 2 would be superior to plan 1. Okay, so it's going to vary from synthesis to synthesis, but since we don't necessarily have the tools to predict the percent yield for individual steps, for us, we will minimize the number of steps in a synthesis. For example, we can take a look at these two paths to the same product. In plan number 1, there's a deprotonation and an alkylation. So but it's overall, it's one step because you deprotonate and then you treat with the alkyl halide. That's why I've combined them. So 1, 2 versus 1, 2, 3 steps for plan 2. So in terms of number of steps, plan 1 would be better than plan 2. And again, just in case it's confusing, I'm lumping these deprotonations and then alkylations together because you'd have in a round bottom flask, you'd have the ketone. To it, you would add LDA to deprotonate it. And then to that same flask, you would add the alkyl halide, whatever that may be, for the alkylation. Of course, this to be done dry ice bath. You would calculate the percent yield at the end of the whole synthetic operation. Okay, so plan 1 is superior in terms of number of synthetic steps. We can also think about linear versus convergent syntheses. So let's imagine that there's 10 steps that need to happen from A to Z. If these happen as a series, a linear series of 10 steps like this, and we'll again pretend that every single step has a percent yield of 90, which is very unlikely. The overall yield of Z would be about 35%. However, if we imagine what's called a convergent synthesis, where perhaps we made intermediate E by the same pathway, but we found another way to take E on to the final product, which involved making compound U and then combining E and U together to make Z. So instead of taking this whole long path to Z, 10 linear steps, you take 4 steps this way, 4 steps this way, and then 1 to combine them. The overall percent yield would be about 60%, assuming that each of these individual steps had 90% yield again. Wow, okay. So we can see convergent, so bringing together 2 intermediates, rather than taking one molecule and doing a bunch of steps on it. Convergent syntheses are often more effective than linear syntheses. Okay, but you probably won't think about that much unless you are a synthetic chemist later in your life. However, environmental responsibility might feel a little bit closer to home and to our interests, and that might also be a little bit easier to conceptualize. There are several principles of green chemistry. I will discuss a few of those here. We can consider the toxicity of reagents and solvents. For example, if we were to look at the 2 proposed routes on this slide, what might stand out to us in terms of toxicity is mercury. Mercury is toxic. So this is another strike against plan number 2. There's a toxic reagent. Not only is it 3 synthetic operations, but there's also a toxic reagent. Halogenated solvents are often avoided as well, but you've probably observed they're pretty common. And in green chemistry, we try to maximize our use of water as a solvent or no solvents. What? That's called neat. If you don't use a solvent, there's no solvent to dispose of. So that's good. Safety of reagents is certainly important. We have discussed the use of diazomethane in cyclopropanation reactions. It's explosive. So certainly we want to avoid that to minimize our chances of having an accident in lab. And we could use instead safer reagents such as the Simmons-Smith reagent for cyclopropanation. Another principle of green chemistry is to minimize waste and byproducts. An example of a reagent that generates a lot of atom waste is MCPBA. MCPBA is typically used in a halogenated solvent, not great, to generate an epoxide. It's an incredibly important reaction because epoxides are incredibly useful synthetic intermediates. However, MCPBA delivers only this one oxygen to the alkene, and then the rest of the molecule is waste, and in fact has to be separated away from the desired compound using a technique similar to TLC, but on a larger scale, and so then that generates even more waste. So another principle of environmental responsibility or green chemistry is to avoid separations. So to, as much as possible, avoid having to do extractions, having to do chromatography, because it just generates more and more waste. I'll just point out one term before we move away, which is that this MCPBA oxidation has poor atom economy because all of these atoms are thrown out. They're all wasted. So that's called atom economy, and you can read more about it in the book. Okay, well, I'm sure I wanted to say much more about this, but this video is becoming long, so you can read about this both in your lab and lecture textbooks. Let's use what we've discussed to evaluate plans 1 and 2 on this slide. Which plan do you think is better, plan 1 or plan 2? Yes, I agree, plan 1. And there is a reason we have not discussed yet for why plan 1 is better than plan 2. Can you figure out what it is? It's a problem with plan 2. So think about it, see if you can figure it out. All right, we'll come back to this. Now again, so when we evaluate two synthetic routes, we can use these principles of efficiency and environmental responsibility. We can also evaluate whether or not a route has synthetic traps. So a synthetic trap is simply an overlooked factor that prevents a reaction from proceeding as planned in the forward direction. Let's consider plan number 2 from the previous slide. I've cut and pasted here for your reference. It was an alkylation of an acetylide ion. This was to meet the parameters of the question that only benzyl bromide and reagents delivering 3 or fewer carbons may be used. That reaction generated this key carbon-carbon bond. Then the alkyne functional group was interconverted into a ketone functional group via an oxymercuration reaction. From there, we proposed the alpha alkylation via the thermodynamic analyte to make the second and final key carbon-carbon bond in the synthesis. So did you figure out where the problem was? Yes, it was in the oxymercuration step. So we'll just put a little danger stop sign around this. The key intermediate is an internal alkyne. Both carbons 2 and 3 are bonded to one other carbon. So during the oxymercuration, the ketone that was desired will be formed, where oxygen adds to carbon 2 and hydrogen adds to carbon 3. However, there is no reason why oxygen couldn't add to carbon 3 and hydrogen to carbon 2, as drawn here. So during the oxymercuration, the atoms that are added are indicated in pink. So oxygen and 2 hydrogens, right? It's a hydration reaction overall. So because carbons 2 and 3 of the alkyne are both internal, they're both bonded to one alkyl group, there is no selectivity here. So for the oxymercuration step, there would be a mixture of products. Well, this would not be good for percent yield, and we'd have to separate them. And we probably couldn't, but let's imagine trying to separate these two from one another. So then you could take the desired one and keep moving. That would be kind of difficult. And they would violate 2 principles here, right? So we want high percent yield step. The maximum will be 50% since these two products would be formed in a 1-to-1 ratio. And a toxic reagent was used, right? So low percent yield, toxic reagent was used. And we have to do a separation to separate those two constitutional isomers from one another. Probably wouldn't work anyways because they have similar polarity, similar functional groups. So as you might predict, it'd be pretty hard to separate these two compounds from one another. All right, plan number 2 was not ideal. That's a nice way to put it. So good thing we had come up with plan number 1. It is the winner. Let's think about the other possible synthetic traps. This one was that there were 2 possible products formed. We'll pause now and give you a moment to consider this question. Propose a synthesis of this molecule from an epoxide. Ready, set, go. There are several possibilities that you may evaluate when proposing a synthesis of this diol from an epoxide. We need to figure out which carbons and which oxygen were part of the epoxide. Let's start by imagining that these 3 atoms were part of the epoxide and that we will be proposing to make one of these bonds. Now, one thing that we could see right away is that of the 2 carbons that we are proposing or part of the epoxide, the more substituted one would be making the new bond. If the more substituted carbon makes the new bond, this must occur under acidic conditions. In order to make these carbon-carbon bonds, that would involve Grignard reagents. So we'll draw a generic example here of how to make a carbon-carbon bond and install, say, a phenyl group like this one. The epoxide is a source of electrophilic carbon. The Grignard reagent is a source of electron-rich nucleophilic carbon. So this reaction occurs under basic conditions. This is the bond that was made. And furthermore, if there was a substituted epoxide, that bond would be made at the less substituted of those 2 carbons. So under basic conditions. Okay, so if the 3 atoms in yellow here were making an epoxide, then we would not be adding a Grignard reagent. So we will not be installing the phenyl group. We will not be installing the propyl group. But perhaps we could install the alcohol group under acidic conditions. All right, what does that mean? Well, in thinking backwards, I'm just pausing for a moment to make sure we can work through this together. And thinking backwards, what I've done is imagined reconnecting here. So we're going to reconnect here and breaking here. Okay, so can we see that? And then, of course, we're going to get rid of this hydrogen. So that's what I'm imagining doing here. Excellent. So now to get to the desired product, we need for water or hydroxide to deliver this group. And it needs to happen under under acidic conditions because the more substituted carbon is being attacked. Okay, so we're going to use tosic acid and water to open that up. That's actually the only appropriate synthetic proposal where these 3 atoms make an epoxide. All right, let's switch. Let's say now instead of those 3 atoms, we had these 3 atoms that were part of the epoxide. And the reason that we thought we might do that is we just really thought this should involve a Grignard reagent. And if we made that bond, we would be attacking the less substituted carbon of this particular epoxide. Right, so this time this one's more substituted, will be more substituted, this one's going to be less substituted. So if we're attacking that less substituted carbon, that occurs under basic conditions. We know that Grignard reagents are basic conditions, so perhaps this will work. We just really feel like we need to use a Grignard reagent. Let's draw the epoxide and propose the reaction in the forward direction. So here you can see the atoms are now bonded. We need to make this bond. So we need to add a 2-carbon piece. So in the forward direction, we would use a 2-carbon Grignard, ethyl Grignard, which would definitely open up at the less substituted carbon. So that part's fine. And then we do an aqueous acidic workup in order to install the proton, the hydrogen, at the formerly epoxide oxygen. Okay, good. Is it good? No, we have a problem. And the problem here is that the Grignard reagent is incompatible with this alcohol that we have in the epoxide starting material. This alcohol is acidic, mildly acidic anyways. It has a pKa of 16, and the Grignard reagent is a strong base. In fact, if we actually attempted this transformation, what would happen is that the ethyl Grignard, which we can pretend is an anion, it's very anionic on carbon, that the ethyl Grignard, so I'm now representing ethyl Grignard like this, okay? It's like a carbanion, it behaves like a carbanion. That would react with this acidic proton on the alcohol, and it would generate the alkoxide anion, and then ethane, conjugate acid. If we say that ethane, the conjugate acid, has a pKa of about 45, then the equilibrium constant for this reaction would be 1 times 10 to the 45 minus 16, so 10 to the 29. Yeah, so quantitative basically favoring these products. And then we didn't open the epoxide. We didn't make the desired bond. So this would not work. So this second idea we had over here on the right side of the screen represents a synthetic trap. We did not think about the incompatibility of an alcohol with a Grignard reagent. So there were multiple reactive functional groups, and the one that we did not want to react ends up reacting. You would just get that alkoxide. So this synthetic route would not work. However, the first one we came up with, it would. So good job, we were good on that. All right, let's try another one. Let's propose reagents for this transformation. This problem is formatted with the starting material on the left and the desired product on the right. We'll begin by identifying functional groups and mapping carbons and considering from what can we make this desired product. We observe the nitrile functional group, a diene starting material, and then an alkene in the product as well. It's reasonable to expect that this alkene is related to the diene, and that if we number these carbons, these are thinking numbers, not naming numbers, this is what we get. All right, so we've added net an equivalent of HCN across that double bond. Now we know no way of doing that exactly, so this must have occurred in more than one step. Well, from what can we make nitriles? Yes, we can make nitriles from alkyl halides. This represents a functional group transformation. From the alkyl halide to the nitrile, we would imagine treating with some source of bromide ion to facilitate an SN2 reaction. Great. Can this alkyl halide be made from the diene? Why, certainly. We know that treating the diene with HBr will yield this alkyl halide product. Hopefully we do have our reaction chart during the red alert in our heads again, because when dienes are treated with HX, so HCl, HBr, HI, there are two possible products. There's the kinetic product, which we desire here. And I'm sorry, I'm going to change the numberings. This was poor planning, but we've added HBr across adjacent carbons, so we'll call them what? This is a 1,2 addition. So we've added HBr across adjacent carbons, which I had numbered 3, 4 in the previous question, but that 1, 2 really means they're adjacent. Okay, so this is versus what's called the 1,4 product, so adding HBr across the ends of the diene. The 1,2 product is a monosubstituted alkane, while the 1,4 product is disubstituted. Thus, the 1,4 product is more stable. It's the thermodynamic product. But if you take a closer look at the 1,2 product, the alkyl halide, the halogen is bonding to a secondary carbon versus a primary. So that means for that 1,2 product, so the transition state to form the 1,2 product has secondary carbocation character, and so the transition state will be lower energy because it's more stable. So at low temperatures, the kinetic product, the monosubstituted alkene, coming from that more stable secondary carbocation-like transition state versus a primary carbocation-like transition state to make the 1,4 product. So we'll observe at 0 degrees the 1,2 product. And at warmer temperatures, such as 40 degrees, equilibration can occur and the 1,4 more stable thermodynamic product is observed. Okay, thank you, reaction chart. Thank you for that red alert. We desire the 1,2 adduct, right? HBr should add across adjacent carbons. So we should carry out this reaction at 0 degrees Celsius. Good job. We didn't fall into the synthetic trap. 2 products were possible, the 1,2 and the 1,4 products, and we favored the desired by controlling the temperature. To convert the alkyl halide into the nitrile desired final product, we will treat with sodium cyanide. Excellent. So this is our proposed synthesis, which we could figure out because we employed retrosynthetic analysis first. Let's try one more. Let's propose reagents for this transformation. We might feel a little bit scared at first because this molecule just kind of looks a bit scary. But here's the cyclopropane. We can also see that there are 4 carbons in both the starting material and the product. So we feel pretty good about that. Of course, there's the CH2 for the cyclopropane, but there's a 4 carbon chain. Seems to map on between the products and the starting material. Cyclopropanes are made from reacting alkenes. So I've drawn the alkene that will correspond to that particular cyclopropane. So treating alkenes with either diazomethane or under Simmons-Smith conditions. So diiodomethane with a diethyl zinc. We talked about this earlier. We're going to use these conditions instead of explosive diazomethane, but either answer would be okay. Awesome, but so we need to think about how to make the alkyl halide from the diene. And hopefully we see that this alkyl halide comes from a 1,4 addition of HCl to the diene. And we said the 1,4 addition occurs at higher temperatures. This time we want the 1,4 product, the thermodynamic product. So we'll treat with HCl at 40 degrees Celsius. It's just warmer than 0. All right, so there's our plan. Now let's write this out in the forward direction. So the diene is treated, as we said, with HCl at elevated temperatures to favor the thermodynamic product, which results from addition of HCl across the ends of the diene. It's called the 1,4 adduct. Then just one more step to get the final product. This is a cyclopropanation. Cyclopropanations are stereospecific, so we can see this trans relationship of the methyl groups in the final product. That trans relationship must also be in the alkene starting material, and you can see it is. These groups are trans to one another. And I drew the trans alkene because that's the most stable conformation. It's more stable than cis, and that's what we expect to observe in the HX addition to the diene. So we'll treat with Simmons-Smith conditions to generate the carbenoid species and ultimately the cyclopropane product. So here's our answer in the forward direction. And this was our plan. There are actually two synthetic traps in this problem. What are they? The first is the issue of the 1,2 versus the 1,4 adduct in the HX addition to the diene. So this is a matter of regioselectivity, or we call it regiochemistry. There are two sites in the molecule that can react, two possible products which are constitutional isomers, and by controlling temperature, we favored just one of those. But if we hadn't controlled the temperature, or if we'd used the wrong temperature, we would have gotten the wrong constitutional isomer of the product. We would have gotten the 1,2 adduct, like in the previous problem. That was undesired this time. And what was the second synthetic trap? It was the stereoselectivity or this of the product, which is trans. So, and also the stereospecificity that the diastereomer of starting material determines which diastereomer of product will be observed of the Simmons-Smith reaction. Then we needed to watch out for that and take it into account. But it all worked out. We didn't fall into any traps. Be sure that you're comfortable with this example before moving on. Let's summarize. The possible synthetic traps we've discussed today are as follows. So there's the issue of more than one functional group. And today we saw the example of the molecule that contained both an alcohol and an epoxide functional group. It was treated with a Grignard reagent. And instead of opening up the epoxide, we would just observe the alcohol being deprotonated and the alkane, useless alkane conjugate acid of the Grignard. So proton transfer reaction, we would not observe the epoxide open product, which is probably what was desired. The second trap is called regiochemistry or regioselectivity, when a reaction can occur in more than one atom of a functional group. For example, with the diene, two products were possible. The one resulting from addition across adjacent carbon atoms, so it looks like just an isolated alkene, versus the addition product resulting from addition across the ends of the diene. So we had to think about this and choose the conditions that favored a reaction at the atom that was desired. All right, what other synthetic traps are there? Yeah, certainly stereoselectivity. If stereochemistry of a product is important, using a stereoselective reaction will be important. We saw this in the final example of the cyclopropanation. Let's take a quick, that probably won't be, look at two more examples. So propose a starting material for each of these transformations. Pause and try yourself. I know you're tired, so take a break if you need to. And then I'm going to quickly explain. The vicinal dihalide comes from addition across two carbons of an alkene. So let's just look at a simple example. If we had our reaction chart out, one of the notes should be that the two bromines add anti. So what we can see in this first problem is that the starting material is an alkene because bromine is the only reagent. So installing these bromine atoms occurred by addition to an alkene. Now you can notice that with the conformation of the alkyl chain like this, so in the anti-conformation, the bromines are syn, or on the same face of the carbon chain. Now we know they added anti, so what that tells me is that the carbon chain is not in this conformation in the alkene. It's not anti, it's actually a cis alkene. When bromine adds, it adds in that anti fashion, forming a racemic mixture of this vicinal dihalide, which then can undergo bond rotation to adopt the anti-conformation of the alkyl chain. All right, so we got to think about stereochemistry there, right? The second reaction appears to be a hydroboration reaction. We recognize those conditions from our reaction chart. We recognize the alcohol product from our reaction chart. And we remember that the alcohol results from an alkene starting material. There is a net addition of HOH across the two carbons of the alkene, where the OH adds to the less substituted carbon. This is called the anti-Markovnikov product. When I say the less substituted carbon, I'm referring to the two carbons of the alkene. And the H and OH are added in a syn fashion. So let's take a look at this product and try to figure out where the alkene was. Let's number all of our carbons. All right, so carbon 1, 2, 3, that's good enough. Those are the only candidates, carbons 1, 2, and 3. So we could have added HOH across this alkene, right? However, if we had, I'm not sure that we could explain the stereochemistry. Also, under hydroboration conditions, we would have oxygen adding to carbon 1 because carbon 1 is less substituted than carbon 2. So if we subjected this alkene to these conditions, we would not get this product. Go ahead and write it out if you need to. However, if we move that alkene, move the double bond between carbons 2 and 3, now that kills that stereocenter, but that's okay. This is a flat alkene. Oops, and we have our aromatic ring. Then that means that HOH would be adding to carbons 2 and 3. OH would be expected to add to carbon 2, just as we observe in the product, because carbon 2 is less substituted than carbon 3. Now let's draw in the H that's added. All right, those are the H and OH atoms that are added across those two carbons of the alkene. Now we have a problem, right? In the hydroboration reaction, they're added syn. So all that means is that this is not the conformation of the alkyl chain when hydroboration occurs. In other words, the alkene actually have the methyl and the phenyl on carbons 1 and 2 on the same side, not anti like they are in this conformation of the product. You can convince yourself of that, but under hydroboration conditions, we would have an addition of OH and H to the same face. So they would add to the top face and they would add to the bottom face of this alkene. So this is a racemic mixture. And then after bond rotation, we would observe this conformation, this diastereomer of the product. So go ahead and convince yourself of that. And sorry, these both should have been listed as racemic. Hope that wasn't confusing. All right, I went through that pretty quickly, but hydroboration and halogenation are both examples where you may have to consider the stereochemistry of products or intermediates. So for example, you could not use the diastereomer of this alkene. This would yield a different diastereomer of the product. Same for the halogenation. We would not use the transalkene. That will give a different diastereomer of the product. So convince yourself of that. And once you've accomplished that, then we should list the reactions for which we should keep stereochemistry in mind. It's many of the reactions that we've learned. So we'll just go through a few just so quickly. So for SN2, when there's a chiral alkyl halide, we know that there's inversion of stereochemistry. Versus an SN1, there will be racemization. For E2, we know that the beta hydrogen and the leaving group must be anti-periplanar. Thus, if these two carbons that are going to become the alkene carbons, if they have substituents on it, this anti-periplanar elimination could affect the stereochemistry of that alkene. Okay, so the stereochemistry will be relevant when it's di or tri-substituted, I guess, or tetra, anything other than mono. And then we'll just generalize here, but all of these additions to alkenes via cyclic, intermediates, and transition states. So this is the second group of electrophilic additions to alkenes that we looked at. Almost all of these will be stereoselective. So we just saw two examples. So with the X2 addition, this is an anti-addition. The hydroboration was a syn addition. So all these electrophilic additions to alkenes via cyclic intermediates or transition states, those are typically stereospecific reactions. So spend some time, make this list, do your practice problems, and do not forget stereochemistry. Okay, this is not an exhaustive list. We can do that together, just not in this video. Let's wrap up. So what should you do now? You should practice. Really, with these problems, you should practice and you should force yourself to use retrosynthetic analysis until it becomes second nature. I have attempted to think aloud when solving the problems today, as I try to do most of the time. So I've tried to model for you how to use retrosynthetic analysis. But the key is to always identify functional groups. And then you can also number carbons. You can map on the carbons in the starting material to the products and use all the other strategies that we employ today. Once you've identified functional groups, ask yourself, what reactions do I know to make this functional group? Activate the reaction chart. So you know these functional group transformations, you know carbon-carbon bond forming steps. You might take some time to just list all the carbon-carbon bond forming steps you know and how you recognize them, for example. And most important is do not invent new chemistry. I love your creativity, but this is not a time to be creative. This is a time to follow the rules. When I write the problems, I asked myself, can they solve it with retrosynthetic analysis? If the answer is no, then I'm not going to ask you the question. So really look at that desired product, whatever it is, and think, what can I make this from? And write out your plan. You'll get partial credit if you can identify correct intermediates, even if you can't get all of the reagents in the forward direction. Revisit the learning goals. Make sure that you've achieved them. I'm not going to go over them now because I actually did a little introduction at the beginning. So go back to the beginning if you want to have the learning goals summarized to make sure that you've got it. But I believe that you do. Summarize and reflect. And congratulations, you're done with Chem 12A. There are 2 practice problems here at the end that I highly suggest that you do, and we'll try to do together in a problem-solving session. Good luck and practice.